All right, so far what we've done is we did simple interest, we did compound interest. What we're going to be doing today is something different. It's related, but it's different in the sense that in compound interest and simple interest, you just deposit something initially at time 0. You would deposit a principal amount when the time is 0. You'll put in a principal amount, and then every year from there, you'll be getting interest on this amount from time 0. Get interest here, you get interest here, you get interest here, it all adds up. Same thing with the simple interest as well. The only difference between these two is that simple interest is always based off of the principal right here, whereas compound interest is based off the principal at time t-1, the previous year. But both of these are based off of the initial principal amounts. What we're going to be doing today is called annuity or annuities. It's denoted by the letter R. With annuities, what you do is that you have an initial amount at time 0. You have an initial principal amount, but every time from here onwards, you are adding a flat principal to the initial principal amount. At time 2, you have this. Well, then you would also have the interest from the P, but then you'd be adding this extra principal. At time 2, you have the initial principal, you have the interest. This is now part of this. I guess I can call this 1, 2. And then you're going to be adding another principal like this. An example would be something like this. Let's say at time 0, you have $500. At time 1, let's say the interest is 10% or whatever, you'll get $550. So this is the interest plus the original principal amount. So here this would be I and P1. But then at this point, you add the same thing as you did before, 500. So your total balance right now is 1150. At time 3, you'll get this 1150. You'll get the interest from it as well. Again, this is compound interest, so it's based off of the previous amount. And you'll be adding something again like this. So your total amount here would be what, 1775 or something. So that's the difference between annuities. At every time, at every compounding period, you're adding the principal back in. So let's see what this looks like. The important thing is to identify what the question's asking us, because there's a lot of things going on here. You have your principal, which is also called the present value. You have your final amount, which is also called the future value. You have your compounding periods. Here it's quarterly, so it's 4. You have your time frame, which is 25 years, which means your N value. You have to multiply that by 4. So your N would be 25 by 4, 100. So what is this question actually asking us? How much will the annuity be worth in 25 years? So which one of these letters are we looking for?
A.
Right, we're looking for A, or we're looking for future value. And here we know our annuity is $500. So this amount you'll be adding into the principal and interest every 3 months. So 4 times a year, you'll be depositing $500 flat. Your interest rate is I, which is going to be 0.052. What do we divide this by? Compounded quarterly, so you divide it by 4. So that's 0.016. This is our compounding period. We multiply 25 by 4. Remember, I you always divide by M, or the number of compounding periods, and N you would multiply by that amount. So N is 100, I is 0.016. we are looking for the future value. The formula for this is right here. Because this question's asking us for future value, we're going to be using this formula. And for the most part, it's pretty simple. It's just a plug and chug. So R is 500 times 1 plus I, so that's going to be 1 plus 0.016 to the power of n, which is 100, minus 1 divided by 0.016, like this. And this will give us the future value if you deposit 500 every month. Oh, sorry, every 3 months. So to plug this in a calculator, I'm going to first plug this, subtract 1, divide by this, and then multiply by 500. So 1.016 to the power of 100 minus 1 divided by 0.016 times 500. So over a period of 25 years, if you deposit 500 every 4 months, this is going to be your final amount. So that's going to be future value if you put away annuity of 500. So just be careful. Sometimes it's going to be an annuity question. Sometimes it's going to be, this is going to be a principal amount. So the difference is that annuity, you're going to be doing it over and over again. So puts away 500 every 3 months. This is your annuity. This is R. Now the next question I can ask you here is, what is the interest that you've earned over the period of 25 years? So this is your future value or your final amount. Your interest is going to be always, your interest is always the final amount minus the amount of money that you put in. I meant to say interest is amount minus principal. This is always going to be the case. But for this annuity question, we're not going to be subtracting 121,000 minus 500. What we do is we subtract 121, your final amount, that remains unchanged, but your principal, you're depositing 500 times. How many times a year? 4 times a year, because it's quarterly. So 500 times 4, for how many years? 25 years. There we go. So this is the flat amount of money that you've put in over a period of 25 years. 500 every 4 months for 25 years. This is your principal, the flat amount of money that you've put in. This is your amount, what it became after 25 years. The answer is just going to be this minus this, and that's going to be the interest earned. So that minus 500 times 4 times 25. So it's going to be 71,584.29 over a period of 25 years. So it's like $3,000 per year, approximately, which is okay, I guess. So that's how we do this question. So here's the formula right here. This comes from, we're not going to get into the derivation because it gets a little bit tricky there at this level, but it just comes from compound interest formula, which says your amount of future value is P1 plus I to the power of N. This is the compound interest formula. And if you add this, if you make a table T0, your amount is P, T1, it's going to be P1 plus I to the power of N. At time 2, this is going to be your principal. And then on that, you're going to be adding 500. On that, you're going to be adding the interest. If you make a table, you add everything up. This is what you end up getting. So that's going to be the bread and butter for the next couple of sessions, annuities. Let's look at this one. So we're depositing monthly. We're making deposits every month. We have the interest rate, 0.096. What do we divide this by? Every month, what does that mean?
12.
So divide this by 12. Quick maths, what's 96 over 12?
8.
Yeah, so it's gonna be 0.008. Let me just double check that. Yeah. Your n is 30. What do we multiply this by?
By 12.
12. That's a lot of compounding periods, 360 compounding periods. What else do we know? We are trying to find the monthly deposit. That's your annuity. That's denoted by R. So this is our unknown. What is our R value? He would like to have 500,000 at the end of 30 years. So what do we denote this by? Is this the amount now or is this the amount in the future?
The future.
Future, so that's going to be your future value. So you want to have 500,000 after 30 years. And this is all we need. So again, we're going to go back here, pull this out, and let's see. So our unknown is R. So our equation is going to look like this. 500,000 equals to R, we don't know, times 1 plus 0.008 to the power of 360 minus 1 all over our I, 0.008. Close bracket, like that. How do we solve this for R? It's just a linear equation, actually. It's the same thing as saying 9 is equals to x times 3. You just divide both sides by 3. Here you divide both sides by this bracket. So let me plug this bracket into a calculator. Whatever I get, I will divide 500,000 from that, and that is going to be our R value. Okay? So it's not too tricky. We just plug this in. 1.008 to the power of 360 minus 1 divided by 0.008. And whatever I get, I'm going to divide 500,000 by that. So the answer here, R, is 240.8. So if you deposit $240 for 30 years every month, you'll have enough to buy a house, $500,000, which is like the median house price. Did that make sense?
Mm-hmm.
Again, the formula is going to be the same. It's not going to change. You just have to be aware of what the question's asking you. It's not that difficult. Unless the I or the N is missing, which looks like that's going to be the case here. So let's see how this works. So this individual borrows 95,000 to buy a cottage. Now think about this. Is this present value or is this future value?
Present.
Yeah, so this is the amount that he borrowed today. So the interest is gonna start accumulating from today. That's gonna be your present value. So this is gonna be 95,000. She agrees to repay the loan by making equal monthly payments. So we have the R value, 750 every month, 12 months. If this individual is, so we have the interest rate, so that's 0.054. And again, remember, divide this by 12. That's not divisible. 0.054 divided by 12 is 0.0045. What is missing? Our n is missing, right?
Mm-hmm.
But remember, we multiply this by 12, like that. So this is what we have. Okay. So how do we solve this? Because the formula that we have right now is for future value. This is what it would accumulate to in the future. But this question is not a future value question. It is a present value question. The book obviously cheats, but we can actually find the answer by using a different formula, which is this one. So this is the formula for present value. Look at the difference between them. R is unchanged. You're still multiplying by R. You're still dividing by the interest I. Now the difference is, in a present value, instead of subtracting 1, you subtract from 1. And this n power, the compounding periods, becomes negative. So that's the only difference. N becomes minus n. And instead of subtracting 1 from this, you subtract this from 1. So let's see if we can use this to answer this question. So we know this is present value. This is going to be 95,000. R is 750. 1 minus 1.0045 to the power of negative n, or negative 12n, sorry. 12n, that 12 plays a part. All over I would be 0.0045, like that. So this is not a linear equation. It's going to be trickier to solve for sure. Our unknown is in the exponent. Keep that in mind. How do we solve this for n?
You divide by 750.
Yeah, that works. So let's divide by 750. We don't really need these brackets then. So 95 over 750. 95,000 divided by 750. That's 126.67. What's next?
You multiply by 0.0045.
All right, so that gives me 0.57 as equals to 1 minus 1.0045 to the power of negative 12n.
You add 1. Or no, you subtract 1.
Yeah, you subtract 1. So you'll get 0.43 negative equals negative 1.0045 to the 12n. The negatives will cancel out. So then you'd get 0.43 is equals to 1.0045 to the power negative 12n. What's the next step?
Logs.
Yeah. So log of 0.43, get to bring the exponent down, negative 12n, times log of 1.0045. What's next?
You divide.
Yep, you divide this by this, and then whatever answer you get, you divide that by negative 12. So log of 0.43 divided by log of 1.0045. So this is gone, this is gone. Whatever answer I get, I'm going to divide that by negative 12. Divided by negative 12. So the final answer is 15.66 years. So there we go. That's how you'd solve this question if the time is missing. It gets a little bit complicated. You have to use logs because the unknown is in the exponent. Is that what they got? Let's see what they got. Yeah. How do they do this? They used Excel. Okay, cool. They used the Excel function called fill down. That's all good and stuff, but can't use this on a test, so it doesn't really help. Let's keep going. Most of them are the same. It's just a formula plug and chug. Um, let's see if we can do this one. So this is our question, and we're going to use the formula for, well, let's see. Let's read the question. Gonna keep both of these on the sides. So both of these ladies, they want to make equal monthly payments. So that should already ring a bell. Equal monthly payments means what? Annuities, right? R. Because compound interest, you're not really adding anything after you've deposited it initially. So they are making equal monthly payments. So we don't know what it is, but we know that M is 12 because they're making monthly payments. N would be 35 times 12. What's that? 420. And there's two different interest rates. For Sonia, we have 6.6 compounded monthly. So 0.066 divided by 12, which is 0.0055. For Anita, we have, what is this? 10.8, 0.108 divided by 12. That's going to be 0.09. 0.009, missed a zero. All right, part A. How much more per month does Sonia have to invest? What is missing? I'll give you a hint. They would like to have this in the future, so it's not a present value question. It's a future value question because they would want 50,000 35 years later. What is missing from the future value formula here?
R.
R is missing, so we need to find two different annuities. One for Sonia, one for Anita, and then whatever we get, we subtract. So let's see how that works. So for Sonia, we're trying to find R. And look at this. To find R, you divide the future value, which is 500,000, I think. What's it? Yeah, 500,000 is the future value. To solve R, you divide future value by this entire bracket. So it's going to be 500,000 divided by 1 plus 0.0055 to the power of n, 420 minus 1 all over 0.0055. Like that. Same thing for Anita as well. The only difference is the R value. 500,000, future value doesn't change. 1, it's gonna be 1 plus 0.009 now, because the interest rate for Anita is different. That's the only difference. Compounding period is still the same. It's for 35 years compounded monthly, minus 1 divided by 0.009, like that. So let me plug both of them in. We're expecting this to be higher than this. It's because it says how much more does Sonia deposit. So we're expecting this R value to be higher than this R value. And it's because she would have to deposit a higher amount because her interest rate is lower. This one's 10.8, this one's 6.6. Because her interest rate is lower, she ends up having to deposit a higher amount each month. So the way I'm gonna do this is I'm gonna first plug this. Whatever I get, I'm gonna do 500,000 divided by answer. So 1.0055 to the power of 420 minus 1 divided by 0.0055, and then 500,000 divided by answer. So this gives me 305.18. Do the exact same thing with this one. 1.009 to the power of 420 minus 1 divided by 0.009. 500,000 divided by answer. I get 106.94. Look at the difference. It's almost $200 more she has to deposit every month. That's about $200. The difference between their annuities, which is a lot of money if you do it every month for 35 years. Part B, if Anita decides to invest the same amount of money as Sonia, how much more money will she have at the end of 35 years? So what is part B asking us? So right now Anita is depositing $106. Part B says if instead of 106, if she deposits 305, right?
Mm-hmm.
What will it amount to after 35 years? Is it going to be higher or lower than 500,000?
Higher.
Yeah, definitely higher. Okay, let's do some paper napkin maths. This is useful in like a restaurant setting. It's not very scientific. I'm predicting her final amount is going to be 500,000 times 3. Where does the 3 come from? Because her monthly deposit is going to triple. So this is napkin math, which gives me $1.5 million. So let's see if this is actually the case. This is the formula to use. So R is going to be 305.18. Now we're doing it for Anita, so it's going to be this amount, 1.009 to the power of 420 minus 1 divided by 0.009. The time hasn't changed. It's still for 35 years, still monthly, so this stays unchanged. Rate hasn't changed, so these stay unchanged. The R is different now. Instead of 106, it's 305. Let's plug that in. Let's see how far off the napkin math was. To the power of 420 minus 1 divided by 0.009 times 305.18. And the answer that I got was 1,426,933.56. So it's pretty close. $1.4 million. Okay.
Mm-hmm.
So there we go. If you have a higher interest rate, if you're investing, that is, if you have a higher interest rate, then your annuity will be lower. On the other hand, if you're borrowing, so let me just make a little table here. If you're investing compared to when you're borrowing, it's just common sense for the most part. You want the interest rate to be high. If you're borrowing, you want the interest rate to be low. You want your R value, you want to be putting less money, right? You don't want to be putting everything. I guess this can go both ways. It depends. The higher you deposit, the more interest you'll end up earning. But this is for sure true. Investment, you want to go with the one with the highest interest rates, but when you're borrowing, you want to go with the one with the lowest interest rates. So you have to do a lot of research because there's hundreds, thousands actually, thousands of banks and credit unions in Canada, and they're not restricted by province. So that was an interesting question. Let's look at 10. Okay, why don't you tell me, is this simple interest? I mean, compound interest? Annuity? If it's annuity, is this a future value formula? Or is this a present value formula? Here are the keywords. 150 every month. Is that an R question or is that a compound interest question? If you're depositing it every month, right?
It's an R question.
That's an R question. So we have the R value. The R value is 150. What do we not have? We don't have the interest. All right, cool. So again, this is the formula. Future value. Because he would like to have, after 10 years, 25,000. So future value is equals to R times 1 plus I to the power of positive N minus 1 over I. We've used this a few times now. This is the formula. The present value, the difference is R and I stay exactly where they are. That doesn't change. But instead of doing minus 1, you do 1 minus. Everything else is the same except that N becomes a negative. But this is not a present value question because he wants to have 25,000 in the future. So from here, we know our future value is 25,000. R is $1.50, 150. I, we don't know. What do we do with our I and our N values? Do we multiply them, divide them? So for the I, because it's being done every month, your
You
M is
divide by
12.
12.
I, you divide by 12, like this, like this. N, you would multiply by 12. So 10 times 12 is 120. There we go. This is our equation. It is not linear. How do we go about solving this for I?
Um,
Let's kill
Divide by
the,
150.
yeah, that's the easy thing to do. Let's kill the 150. That gives us 166.67 is equals to, what's the next part?
You multiply by I over 12.
I don't know if this is doable by hand. Because you can add 1 to it. Like that. But now we've hit a brick wall. We could take the 1/20th root here and get rid of this. But then again, we can't, there is no way, there is a way, but we're not gonna get into that. There is no way to combine, this is linear, it has a power 1. This is a polynomial, it has a power what? 120, right?
120.
There is no easy way to combine to the power of 120. If it was power 3, 4, 5, I guess we could do synthetic division, this, that, try to make it easier. But as of right now, this is not doable. If you want to do this, there is a way. This is very advanced. This probably you'll see in like third year, maybe math course at university. You can use something called, I'm not going to get into this because we haven't done the prerequisites, but you can use something called Riemann's zeta function to answer this question. Maybe this is for your own curiosity if you want to watch or Google this later. there's a function that allows you to combine linear functions, like something like this, with higher degree polynomials. 120, this doesn't really matter. This could be 10,000. It doesn't really matter, but it allows us to combine these. Um, I don't see any easy way to combine these two. So ultimately what this is essentially is this is a calculator problem. By calculator, I mean a graphical calculator problem. So what we're gonna do is we're gonna chug these in and let's see if we get a good result. So this is on our left side. On our right side, we have, gonna need a bracket here. It is 1 plus was 1 plus I over 12 to the 120. So 1 plus x, it doesn't understand I, so you want to do it like this. So let's see if they ever meet, or maybe I can just, yeah, no, they do. Right here. So you set them equal to each other, and the answer would be your x-intercept. So right there is your interest rate. 6.3% essentially is what it is, okay? See this?
Mm-hmm.
It doesn't tell you exactly what it is. It's probably 6.31, 6311 or something. But that's going to be interest rate. There's no easy way to do this by hand. I'm surprised it asked you here, probably because they want you to use Excel to do this. In Excel, the idea is the same. You just put this in one cell, put this in another, and you click solve. It'll give you 6.3%. Desmos is easier though. So there we go. That's how you do this one. No easy way to do by hand. In 15 minutes, let's move on to present value. Again, we've seen the formula. What it is essentially, you just want to read the question. Again, they're using a spreadsheet here. Let's see if we can do this by hand. I'm sure we can be. The only instance you can't do by hand if it's the I is missing. She won a lottery. She won it. Oh, this is actually a real life question as well. So this applies to every lottery that you win. In the US, this is the difference. The lottery winnings are taxed. So you may hear like there's a $1.1 billion Powerball or whatever, right?
Mm-hmm.
Depending on the, well, in the US, depending on the state, there's going to be some federal taxes that you have to pay, and I'm sure you have to also pay state level taxes. So it's taxed. It's a lot. The way tax brackets work is it depends on how much money that you make. I don't know the exact figures, but it works something like this. It's not 50,000. I think it's 30,000. If you earn this, you're taxed 5%. Between 30,000 and again, these are just hypothetical amounts, but it's something like this. You're taxed 7.5%. Between 50,000 to 100,000, you're taxed 10%. And it keeps going on and on and on. But something like a lottery, which is worth millions of dollars, you're taxed a third. And this is napkin math, but you're taxed around a third of your winnings. So even if you get $1 billion, you can only take home, it's probably more than a third now that I think about it. You'll only take home $700 million if you win a billion. But this is not the case in Canada. In Canada, they are not taxed. So if you win a lottery, it's better to win it in Canada because you don't have to pay any taxes. And when you do win a lottery, you have a choice on how you want to collect that amount. One way is that you take that amount, whatever it is, like in this case, it's 50,000. You take this amount on day one. You cash out all of it. In the US, you cash out all of it minus the taxes on day one. This is called the lump sum. The flat amount is called a lump sum amount. Alternatively, what you can do is this. Instead of cashing out $50,000 on day one, you can cash out, what is this, 20 years? Again, this is not exact, but it's gonna be like 25. There's gonna be interest on it as well. You cash out $2,500 plus some interest. So let's say that's almost $3,000. You cash out $3,000 a year for 20 years. So at the end of 20 years, you actually end up getting what, $60,000. Which one is better? Is getting $50,000 on day one better, or is getting a slightly higher yearly amount each year for 20 years better? Because at the end of the 20 years, you'll get 60,000. What do you think? Which one would you go with?
The first one?
100% the first one. This is actually a scam. It's not a scam, but this is really bad. This you want to do if you're not good with money. Let's say you have a gambling problem or something like that. Then you want to go with this one, okay? Because if you put this amount on day one at 5%, you'll end up, what is this, over a period of 20 years? Remember, money doubles almost 6, 7 years, money doubles. You'll end up tripling it. You'll end up more than tripling it over a period of 20 years. So look at this. This is a trap, okay? You don't want to be doing the monthly payment for various reasons. One of them is this one. Flat out, if you take this, you invest it, you'll get way more than you would from this. That's number one. Other reason is this, because whatever the paying entity is, the company, right? Whatever
Mm-hmm.
is Lottomax, whatever, all these lottery companies, they may not exist for 20 years. They may exist for 5 years, 10 years, and then they might crash. They might file for bankruptcy. You won't get any further payments from them. So there's a lot of uncertainty about the future of the paying company. So that's another reason you don't want to be doing this, the bottom option. Lump sum is 100% the way to go. Like I said, there's some very rare instances where you don't want to do this. One of them is a lot of people, lottery buyers are usually gamblers. So if you have a problem, you may want to go with the yearly option. But not a lot of people do. Most people take the lump sum because it's common knowledge that the other option is will rip you off. So anyways, going back to this question, what is the question? So we know our present value is $50,000 and our time frame is 20. It's compounded annually, so it doesn't matter. No need to times 1 divide by 1, no change. Interest rate is also unchanged, 0.05. What do you think is the missing component here? What is missing? What is the question actually asking us? So we're making a choice, yeah?
Mm-hmm.
Making a choice between the lump sum or the yearly rates. So the way you want to approach this is that you want to think of it from both ways, I guess. So here's how you'd solve this. Should we use technology? Probably not. All right. So 5% compounded annually. Let's see what the future value is. If this money, you put it at 5% compounded annually, then you're just going to use the compound interest formula. And let's see what this gives us. So 50,000 times 1.05 to the power 20. So like I said, it almost triples. It's going to be 132,664.89. So this is the first case where you take the lump sum and you throw it into a bank account. Throw it in an investment in a bank, whatever works best. Bank account for 20 years. This is what it would amount to. This question is asking us, what is the R value that's equivalent to getting this in 20 years? So the second half of this question is no longer a compound interest problem. It's an annuity problem in which future value, that's not your future value, that's your present value, is 50,000. This is the amount that you have today. R is missing, N is 20, I is 0.05. Then you want to use the present value formula here for this one. Because we're talking about annuities dependent on the present value. So the formula is this. Present value is equals to R. There's an I down here. You always subtract from 1 when you're doing present value. And the N is negative. This is the formula. So your present value is 50,000, right?
Mhm.
I don't know if I did it right. I don't think I did it right because this is 50,000 a year for 20 years. So what would that be as a lump sum? Oh no, this is not right. Lump sum amount. This is considering if you only got paid once a year. This is not gonna be the lump sum amount. The lump sum amount would actually be
It's a
this.
million.
It'll be 50,000 times 20 straight up, right? Yeah,
Yeah.
yeah. That's $1 million. 500, yeah, that's $1 million lump sum. So this is the amount that you would get here, which means that is how much your money would be worth. So that's gonna be 1 million down here. There we go. Present value is actually 50,000 times 20, 1 million. Nothing else changes. R, 1 minus 1.05 to the power negative 20 over 0.05. Gonna plug this in a calculator, divide both sides by that. 1 minus 1.05 to the power negative 20 divided by 0.05, 1 million. Divided by answer. So that gives me 80,240.58. So there we go. Now think about it. If you take the lump sum, yeah? If you
Mhm.
take the lump sum today, it would be as if you're getting paid $80,000 a year for 20 years. If you take the lump sum, that is the equivalent. But this, you're being offered 50,000 for 20 years. So would you take the 50 grand or would you take the lump sum? Because if you
So
take the lump sum, that's worth 80,000 a year, right?
yeah,
So which one do you go with? Go
the
with the lump
second
sum.
one.
Definitely go with the lump sum, this one, because it's worth $30,000 more. And again, this one, what you want to do with this is this $1 million, let's just see how much it's going to become in 20 years. It'll be a huge amount. So let's say we have $1 million, we plug it in a bank account that pays us 5% interest annually for 20 years. You can find way better deals than this. With this amount of money, you can find way better deals than just 5%. But this is going to be your bare minimum. 1 million times 1.05 to the power 20. You end up getting $2.6 million. You see that?
Mhm.
This is a scam. You see how big of a scam this is? This doesn't even cover the million, because a million would be 80,000. But actually what the million actually amounts to would be 4 times as much. 80,000 times 4, 320,000. So this is kind of your ceiling, your limit. They're offering you the bare minimum. So do not go with the monthly option if you win a lottery. But this applies real life as well. All right, let's just call it there for today. That was a big question.
Okay, thank you.
See ya.